I have big shoes to fill after all this, good stuff. You see what really works, what's here, what's available, and so on. And now I'm supposed to talk about something that's coming. And like you say, I agree. We don't even have all the 11ax features implemented. We are barely talking about 6 gigahertz 11ax. And we are already pushing BE. So I cannot show you measurements like some other people did and so on, but I did work hard to find some simulations and some research papers where some people, PhD candidates of course, were actually already running some simulations about parts of the 802.11be, and that is multilink operation. Now, it's not, I noticed in these 2 days that it's not really a practice here in this room to thank other people. Of course not, because we are professionals. Why would we even say thank you? But I do say thank you. I'm standing on the shoulders of the giants. Some of them are here, David. Some of them left this morning and so on. And there are so many others, not forgetting Keith and many other people. Thank you so much. I'm here, and I know because of the community like you and because of the support from you and support from my companies, current and past. Now, talking about 11be to add to this, hard to talk about what's coming, what's really, going to be in the final draft. We are at draft 1.3 right now. But what I think, why is such a push for this BE now is, I think that Wi-Fi, regardless of this economic value that it creates for the world, regardless of how many devices are in use. I don't know if you can see this number, but 18 billion Wi-Fi devices are in use, with 7.7 billion people on Earth. That means that every person on Earth has more than 2 devices already. So still, with these impressive numbers, I do agree that we feel a little pressure from 5G and marketing around 5G and how 5G can now satisfy requirements of the new things that are coming. And these new things are called with a fancy name AV and XV and so on, right? Augmented realities and virtual realities and all these things. So 11be should actually work on improving things so that certain things that these new applications, new uses require. And as the standard or draft standard says is that it will enable at least one mode of operation where the actually bit rate, the data rate will be at least 30 gigabits per second. That sounds really high. And the frequencies between 1 and 7.2 gigahertz, while ensuring backwards compatibility. So IEEE and Wi-Fi Alliance are doing a great job assuring this backwards compatibility with the older devices. And another one, the last one, is this amendment defines at least one mode of operation capable of improved worst case latency. Why I'm showing you this? Because when I show you a little about this multi-link operation, you will see how multi-link operation tries to satisfy all these 3 requirements that you see here. And here is the timeline. Timeline is also a little different than we used to see with the previous amendments. As you see, expected ratification is 24-25, which is extremely ambitious target. And because of this ambitious target, two things happened. So one thing that happened is that task groups are now physical layer task group that is separate from the MEC layer, data link layer task group, so they can work in parallel. But because these two groups work in parallel now, they agreed on so-called two phases or two releases of this amendment. And here you see the list of features that are probably currently, maybe it has changed in the past 2 weeks or something, but that are currently scheduled to be in release 1 and release 2. I put this here on purpose because we can list the features by different criteria. Many of these features are actually just evolution of the previous amendments. What are those features? 320 megahertz channels. It reminds you about 40, 80, 160, and of course this is 160 plus 160 or 320. So it's just kind of evolution. QAM, 4096 QAM. Isn't that just evolution of how this QAM was getting more and more tiny or bigger, whatever way you want to look into it. But there are definitely some features here that are new, and one of them that is expected to be the cool feature and the one that will really deliver on what B is all about is a multi-link operation feature. So what is the objective of this multi-link operation feature? Not of the amendment. Amendment has so many features, but of this multi-link operation. So there are two objectives stated, and I kind of see the third one also. So increase the data rate. We are back to the race that we know from A and B and so on. Go faster, go faster, go faster, except AX was more about efficiency, okay? So increase the data rate and then lower the latency. We keep saying that, lower the latency, but augmented realities, virtual realities, name it, they really do many times require very low latencies. And I see that increased reliability can also be something that we will get from multi-link operation. And I will show you why I think that this may be, maybe even the first thing that we get out of it. And when you are thinking, when you hear multi, yeah, there's multiple link operations. What does that mean? In the simplest possible form, as you see, is today access points have at least 3 modes of operations. They have either 2.4 and dual 5 gigahertz, or they have 3, 2.4, 5, and 6 gigahertz radios. Do you think that the air is really busy? Well, yeah, you have all these cool tools where you show how busy the air is. But when you are really honest, you can say, well, it's not really busy. It's so much weight. It's just the nature of Wi-Fi, how Wi-Fi works. Which means that I have all this weight. What if I start using better, if I get better usage of at least one link, and if I have 2 or 3 links, can I put them together and I have this huge super highway and I can deliver on higher data rate, I can lower the latency, and I don't know about reliability yet. So, and then the same on client devices. Client devices today, they also have 2 interfaces, 3 interfaces now. David just mentioned hundreds of 6 gigahertz client devices being available. So maybe we can really make something better use of the airspace. So when you think about multi-link operation, I think about multi-band, multi-channel, not just multi-band, also multi-channel, reminding you of dual 5 gigahertz, right? And what are the current challenges, really? Not just that the air is not necessarily busy. It is also that when you have wider channels supposed to deliver the same things. We always say that, oh, you have higher data rate, higher throughput with wider channels, you have lower latency because more data is delivered and so on. What's the problem? You just saw this morning what the problem is, right, with these wider channels. First, they are all dictated, if I can say so, by the primary channel. And if primary channel, first, it has to be available. If primary channel is available and secondary channel is not available, here is your 80 gigahertz. How much did you waste? 2/3. 2/3 is wasted because only the first 20 megahertz is available. Is that true? Of course it's true. We are not in a cave or on Mars where there are no neighbors and nobody around. So this is probably very realistic situation. Second thing is wide channels need more power. They use more power. So with access points, yeah, sure, bring BT to the edge, you know, your access points will get power and all these things. Well, we can do that, but what about on your mobile device, right? How much power, how often do you have to charge? How do you charge it? You know, if you have 320 megahertz channel, how long will that battery last? Say with the peak to average power ratio growth, the wider the channel, more OFDM tones, you know, greater power usage. And when you start thinking 160 megahertz or 320 megahertz channels, what you find is, I mean, this is a wide spectrum. And maybe some parts of this spectrum have interference, or they have different interference levels than the other parts of this very wide spectrum. So what does that mean? Well, I hear you, I don't hear you, I hear you kinda, okay, and so on. So if we go just with the wider channels, we are simply also just increasing the problems that existed before. So with this multi-link operation, what are the use cases? The use cases that we see are, first, this could be a way of doing band steering. We used to have band steering long ago. It meant that when client device was probing and trying to associate, we were ignoring the device on 2.4 gigahertz, so device would go on 5 gigahertz. So that was sort of band steering, even load balancing and so on. And if it happened that even during the session and so on, I know at least one vendor that had implemented this. If vendor somehow artificially, you know, moved the client to another frequency, there was always repetition of the management process. Right? And that means that it was not fast enough, and all these things. So with multi-link operation, the idea is not to do this kind of a band steering. The idea is just move them from one link to another link without repeating any of the management process. And that could be also used then for load balancing. Load balancing can be used between the links, between the bands, or it can be even used for certain applications, because now the idea is, oh, there are certain applications that need different conditions. What if we just move that on another faster link, 6 gigahertz, and so on? Other ideas, other use cases of multi-link operation are aggregation, right? That's probably the first one that comes to your mind. Now I'm going to use all 3 links, and when I can use all 3 links and put together max 2.4, 5, and 6 gigahertz, you will see you exceed 30 gigabits per second, like the standard says. You are approaching 40, 45, actually, gigabits per second, right? Is that realistic? Of course not. But, this is what in marketing we will use, of course. So, so aggregation, that can be idea. I have this critical application, I'm hospital, it's whatever application in the hospital. Ooh, I need now a lot of bandwidth, so I'm going to use all 3 links. And there is another use case that I kind of hinted earlier, that is reliability. Now, if I have 2 or even 3 links, what I can do is I can duplicate the traffic. So I send the same traffic over all 3 links. What do I get? Nothing but reliability, right? Now my link is solid because hopefully at least one will finish, and it will finish fast. Right, so that's why I'm mentioning another maybe possible use case of this multi-link operation. So for multi-link to happen, now we are talking about using different frequency bands, or if it's same frequency band, different channel, to be exact. Something has to change because we are talking physical layer, then we have layer 2 or data link layer, and we have layer 3 with IP and then TCP and so on. If we want to play with these ideas of multi-link, we should leave IP, TCP, and all the other layers completely intact. So to them, everything should stay the same. But what we really need, because data link layer is the one that talks to the physical layer, what we really need is we need multiples now suddenly. This is not one link anymore. So that calls for basically very dramatic, to me, very dramatic change of the MAC layer. And in the MAC layer, we now have 2 MAC layers. One is UMAC or upper MAC, and the other one is LMAC or lower MAC. And the upper MAC keeps the traditional, MAC functions like frame sequencing, MAC address. It's only one MAC address, regardless of how many links you have below, one MAC address to the upper layer. Upper layer will do association, link setup, association, authentication, and all these traditional functions. But lower MAC now will have link-specific information. What is link-specific? ETCA queues. ETCA queues. Every low MAC, for every link, will have its own ETCA queue. Management and control frames are created on this layer. Frame headers are created to transmit or validate it on the receive side, and so on. So you see, we kind of split the MAC now so that we still access the physical layer and that we keep upper layer intact. Some more terminology. So this amendment specifies MLD, multi-link device. And that's just, of course, device that is capable of doing multi-link and blah, blah, blah. But there are 3 operating modes of devices that are also defined. So it is single link operation. These are the devices that you already know. It's one link. frames are numbered, they are sent out in sequence, and all these things. What is new is STR, simultaneous transmission reception. That is device, MLD device, that has at least 2 interfaces, and that these interfaces can be used to transmit and receive at the same time. I'll talk a little later, hopefully, about how the links are established. You will see what it means that first available band is assigned. And then there's another MLD device called NSTR, non-simultaneous transmission reception, which means that device has 2 or more interfaces, but these interfaces are not completely independent like in STR. They are dependent in a way that one gains access to the network, and then the other link is checked if it's available, and then they can transmit. So it depends on the primary. Once the primary gains access to the network, the secondary is checked. So why does this matter? There are also 2 modes of accessing the link. Default mode is asynchronous mode, and asynchronous is the one that should bring all these advantages, right? I have 2 links, I can use them for downlink and uplink at the same time. They are independent, they have their own queues, they can do whatever they want, and life is beautiful. Well, life is beautiful until the IDC interference happens, inter-device coexistence interference. Yeah. That is interference that we already know from dual 5 gigahertz. If the channels are too close, there is a power leakage, and that means a lot of problems. So this may happen now on multi-link devices. And to work around this problem, synchronous multi-link solution is proposed. So that is for non-STR stations, and this synchronous access has single and multi-link primary channel access schemes, because with synchronous non-STR devices, the primary channel gains access, and then we go, oh, so primary channel has access. Let's see if the secondary, the second link, is also available. If it's not available, well, we will probably have to wait on the secondary. And while we wait on the secondary, we are also holding back everyone else on the primary, because their countdown timers must freeze, right, when I gain access. So there are 2 ways of how is this situation handled. One is that single primary is found and is probed, and then when it gains access, the secondary is checked. The other scheme is, oh, let's just keep probing and listening to the network, on all the links, and when one link gains access, we will start changing, we will start scanning and waiting on the others. This is just some terminology and so on, also to help you understand later why our performance is not as maybe expected. How are the links established? So there's one cool thing from IEEE, that they agreed not to develop another 24 of new frames and frame types and so on, and they agreed to reuse existing frames for links establishment. There are some changes needed in traditional link establishment, and that is new information element called multilink element, surprise, is introduced. And there are 2 types. There are 2 types of this multilink element. One is basic type that you see used in beacons. What it does is just simply advertises the common, the upper MAC information, and there is a response, request-response type of the multilink information element that actually carries the link-specific information. Without going into the details, now, when you imagine, you all know how devices connect. So now client device is probing, and it hears the beacon that says I'm multilink capable, and here's my multilink ID, and that's it. Now, client device has to keep probing more and more, has to go or listening for the beacons through all the links to be able to put information together. Aha, I have now these 3 links that I connect, that I can use to connect to the device. So instead of wasting all this time, because this increases management traffic dramatically, reduced neighbor report is reused. And reduced neighbor report, as you see, actually carries very basic information about the other links that exist, so that client device can basically just go straight to those links. It's a lot of information, it's a lot of details. I'm sorry to bother you with this, but you are all geeks and professionals, so you may appreciate. There are much more details. So with multilinks, another problem is client devices, again, having 3, imagine asynchronous STR going on. So you have 3 links possible, you have transmit and receive happening on all the links. Awesome, life is beautiful, it's so fast, but your battery will last for 2.5 minutes. So power save mode is more important than it ever was. And also with the power save mode, there are not so many changes, or maybe there's not enough work done yet. The changes are team traffic indicator map is extended with the link information, another bitmap. Oh, my bit is on, let me check which of the links has data waiting, and let me just awake that link, right? Target wake-up time agreements are also proposed. Again, more than one variation of target wake-up time is proposed. So one says, that's the one that you see, one says that only one link will be used for this TWT information, and that one link will carry information for all the other links. There are also proposals that every link will have its own target wake-up time, because they may need different target wake-up times. Talking about applications, so I keep repeating augmented realities, virtual realities, and so on. They need either ultra low latency, or they need really reliability again. So this is just 2 modes or 2 ideas also proposed how to help real-time applications. So the first mode is duplicate mode, where the same traffic is repeated on all the links. When the first transmission is completed, all subsequent packets are dropped. Or joint, where we don't get reliability, but we get ultra low latency. And conditional, I think, is also proposed, which is, in my mind, the worst, which means do joint, and if you are not successful, try again, and if you are not successful, do duplicate, or something like this. Now, the promised, I'll go a little longer because the other guy was too short. So please give him the promised break. So So the only measurements that I was able to find are from Rice University in Houston in cooperation with the Barcelona University. And these guys, I'll show you later, they did some real measurements and then simulations of this multilink. And let me quickly show you how it looked. So basically, they were really collecting channel information at the Barcelona soccer stadium. You know the club playing there. If not, shame on you. So basically, this is the real life, and their information is publicly available. All this data that they collected at this stadium during the game is available in so-called WACA, W-A-C-A data set. It's available on GitHub. If you're interested, you geeks, where you're playing with the data, I can share the link with you how you get it. Anyway, what they did is they collected all this traffic, and then they simulated 3 devices. As you see here, devices are single link operation, they are multi-link operation STR, simultaneous transmit and receive, and non-STR, where it only happens in parallel. And the first simulation they did is they also normalized the traffic. I'm not going to go into details of statistics, what it means, but they were using only downlink, and all the packets, simulated packets, were the same size. And they looked into the symmetric occupancy of the channels. As you see, all the channels were either 10% occupied, 40%, or 70% occupied. And they ran this normalized traffic. And what do you see? Well, it is pretty expected, isn't it? Single link operation latency increases like crazy as the channel gets busier and busier. And then the STR performs better than non-STR. Is that expected? Yeah, simultaneous, transmit and receive kind of sounds better than find one and then wait and then do the transmission. So I don't see much surprise here. It is expected. It is 95 percentile 2, which, if you remember slide 1 about this amendment, says worst case scenario. 95 percentile is as close to worst case as it gets. But let's look into this one. This one doesn't have symmetric channel occupancy, which is more real life. And what are assumptions in this simulation? So first, you see that primary channel is considered less occupied. Secondary is more occupied. And then let's look into the results. First, in the first one, you see that STR is detrimental to non-STR. Wow, how did this happen? STR should always be the best. I have 2 completely independent links. They can do transmit and receive whenever they want. They have their own queues, everything. Well, it didn't really come out like this. The second one is even worse, where STR, the most promising one, is even worse than single link operation. Any idea why this happens? Any idea why this happens? Well, how do devices access the network, right? How do they access? At one point, it comes to the, what's the last one? Counter. And what happens when another channel is occupied or another transmission happens? You have to freeze, wait, there you go, kid. Yay, right? You have to freeze the counter. Aha, now that I freeze the counter, every time I have to freeze the counter, I also have to increase my counter. There you go. There you go. So this is what happens here. Freezing happens. Because the other channel, which is secondary channel, which is more occupied, is occupied, and I freeze. Right? So it is very interesting, it's very real life, it's very eye-opening, and it may be just another of the multi-features that may not deliver as much as we expected. So what's next? Yeah, I know, 5 minutes. I'll be really short. So what are still open? What are still open issues? So I did not talk yet about the real life environment, which is tons of old devices, legacy devices that don't understand Multilink, and their blindness. They don't see maybe transmissions happening because they listen only on one channel and they understand only one channel, right? Then spectral inefficiency with synchronous transmissions. It's the waste. Get the access, wait on the second channel or the second link to become available. It's not efficient, no matter what they say that this is for efficiency. Channel access fairness also. If I have asynchronous and I'm taking both of them, how will the old devices or non-STR devices gain the access? Again, freeze the counter, double the counter, and all these things. Load balancing. There may be, different ways of doing load balancing, not just by application. They may be by traffic QoS requirement. It may be load balancing by uplinks and downlinks and so on. There are still many options open. And the one that worries me the most is, how am I gonna know how I should actually now enable these features? How will these features interplay with each other? I think you've heard about the preamble puncturing and so on. There are so many more features in BE. And then you have AX features and multi-user MIMOs and all these things. How are they going to interplay with each other? What combinations shall I enable and so on? Is it even humanly possible? Or we need this buzzword, which is data science and AI ML, to help us figure out how to configure this. Thank you.